Okay, so next is going to be Jeff Nkashama. Okay. I apologize if I pronounce your name wrong. So he's going to speak about deep learning for network infection and the data contamination, evaluating robustness and mitigating performance degradation. So this only.
Hello everyone. I'm Jeff Nkashama, and I'm a PhD student at the University de Sherbrooke in Canada. And yeah, I'm going to present to you our work on deep learning for network anomaly detection under data contamination. This is a journal in our research group. Yeah, so we are at SECAI, and we are today witnessing our AI has revolutionized many domains, and we see that more and more AI is also being adopted in the cybersecurity industry because it enables analyzing large amount of data and to do that in real time and save time, also reduce workload from cybersecurity experts in tasks like doing threat detection or incident response and many others. And particularly for tasks like network anomaly detection, deep learning has emerged as a crucial tool. And talking about anomaly detection is a task that consists of identifying observation data or events that deviate from what is deemed normal. So it means that the way those anomaly detection models are trained is you provide data related to the normal state of a system. Like for instance, here we're looking at network traffic. So you provide normal data related to network traffic, and the model will learn why normal patterns those data and assign a score to each data point provided as an input. And when it comes to inference, once the model is flowing, then breadpoints there, which represents some anomalies. And given some threshold, the model should be able to separate normal data from anomalies using the score that it has learned from the training process. But there is a problem in the way I just presented the anomaly detection task because there is a strong assumption here that during training, the model will receive only normal data, which is expected to be clean and not contain anomalies, malicious data. But in real world, we cannot guarantee having such a training data set. So that is really a problem. And as the volume of data grows, it becomes complicated and difficult say it's clean because one way this can be resolved is by labeling data, but that would be expensive given the amounts of those data. And potential sources of such contaminations in the training data sets can be maybe during data collection, there was already an attack campaign going on, and that will be collected also as normal data or some misconfiguration. Also, we can have a compromised equipment in the network, and that will generate data that will be anomalies in the training, or also in adversary can try to inject malicious data in the training set. And that's a problem. So in our work, we try to evaluate how deep learning models for network anomaly detection will perform when that strong assumption of having clean data sets is violated. So we've selected a wide range model here, generative one, those based on reconstruction errors, and also we have one model based on self-supervised learning. And yeah, to do that, we also design evaluation protocols to evaluate the robustness of those models in a way that, rigorous way, and also in a way to prevent data leak during evaluation process. And we also propose a way to improve the autoencoder, which is one of the most used anomaly detection, deep learning based anomaly detection model by adding a constraint in the way it's trained. I will just talk about it in the next slide. So an autoencoder is a deep learning model that basically tries to reconstruct its input. So it takes in data points, then will project that to some latent space, and using usually the latent space reduced space, so it's a kind of compression, and we'll try to reconstruct that compression. So the way it's trained is by minimizing the difference of the original inputs and its reconstruction. So and then in anomaly prediction, will use normal data, learn to reconstruct them. And for an anomaly, so data point that wasn't in the training set, we will expect this value in the loss function to be higher than those in the training set. So the way a standard anomaly detection model is, autoencoder is trained. It's only, the training is only led by the reconstruction error, but inspired by what we have in like NLP with embeddings, we say that if we are projecting normal data in the latent space, we will expect that those data points be in some like dense area in the latent space, as it is the case for embeddings for words, for instance, in NLP. So we'll expect the same with anomaly detection. So instead of just having the reconstruction error to lead our learning process, we also added here a constraint in the optimization, so that when we project the input data points into the latent space, we enforce it to be centered to some center in that latent space, and we will try to minimize the difference between those projections and the center in that latent space. And here we try to apply this optimization using some 2D synthetic data points here in the next plots there. It's when we have, it's related to the standard autoencoding. And we can see that the lower is 4, normal is the point. So we can see that when we use the standard data points, the model is really performing bad. When the training data set contains also anomalies instead of having just normal data. And in the middle, it's using the constrained autoencoder that I just presented. But in the middle, we say we enforce all the data points, the latent representations of data point to be centered around the mean of all the latent projection. And we can see that it's a little bit better on state compared to the standard version, but still we have so many false positive points. And then for the plots here in left here, it's when we do not have like use a specific center, but we let the model to figure out what should be the right center of those latent representations. So and we can see that it's improving. So we've decided here, instead of imposing what should be the center in that latent space, will make the center to be a learnable parameter during optimization. And the model will have to figure out what is the best one. So here is the evaluation protocol that we use for one or a single run. So yeah, the benign data set is split and part is used to training. So training is expected to contain only benign data set, but we here introduce malicious data into that training set to violate the hypothesis of having clean data. And we do that by creating a set here that we call a contamination set, where we will be taking anomalies and injecting them in the training set. And by doing it this way, we ensure that the test set, the proportion anomalies and benign data in the training set will remain the same. And also, instead of using the test sets to compute threshold, we suggest here that the threshold should be computed in some other sets, and then the test set, the final test set, should be used only for evaluation, yeah, compared to what we've seen in the literature, and that will help to avoid to have a sort of data leakage, because we will have only we already have some information on the trainings on the test sets if we use it directly to compute the threshold which is necessary to the task of anomaly detection classification. So here are the results that we've got. And for the plot E, this is an evaluation on the KDD dataset, old dataset, but unfortunately, we keep using in the community. So in that dataset, you can observe that almost, all the models except the GMM are performing quite well, even when we increase the contamination ratio in the training into the training set. But like the last one, the last one see here is the evaluation of the CICIDS 2018 data sets. And from there, we can see that increase the contamination rates, the performance, and the performance here is what efforts is dropping. But for our proposed trick of having a constrained training of deep autoencoder, those models which are DAE-LR here and DUAD-LR here, they are still performing top out of model. So it shows that adding that constraint help a lot in the case of when the training set is contaminated. And yeah, so we try to represent, we try to understand why was it that in the old KDD data set, the model was performing good even when we increased the contamination rate. We projected the data points, those data sets into a 2D space. We use a Disney representation. And for there, we can see that there are less overlapping points. So it's showing that the attacks in that KDB data sets are much, I would say, easier to detect compared to the plots in my left here, where we have many overlaps, and it shows that how the attack vector have evolved by the time over the time, and they become more harder to detect. So that's why when we have contamination using those recent data sets, they really impact the performance of models. And we also evaluated those models on some other data sets, IoT network data sets, and CI statistics 2023. So even from this one here, we have still the DA error. So using the trick that we propose and dual error that implement the constraint level application, they are still performing the top, but still the F1 score is really dropping as we augment the contamination ratio in the data set. So this shows that this problem is really remaining like important and need to be solved. Yeah, through the constraint representation helps to still perform better, but yeah, overall the performance is dropping. So yeah, so I think I've already talked about this, and we've also run a statistical test after doing all the experiments with all the contamination ratio. Then we've got some statistical tests to run the model, and here we can clearly see that having the trick again, the constraint latent representation has helped the GUAD and autoencoder model to perform well. So they are ranked at the top of all the other models. But yeah, we also observe that there are some other models, generative models like ALAT, which are also good, performing well, but yeah, often in cybersecurity, we see many works using mainly deep autoencoder, but other models from also self-supervised learning models are doing quite well and may require also attention. So that will be what can conclude. It's as I said, we have no guarantee with clean data sets, training data set when doing anomaly detection or network anomaly detection. And yeah, in real world, we can still have anomalies data into the training set. And it's important to really take that attention when developing new models. They have to be robust and be tested also in setting where we have anomalous data into the training set. And yeah, in our work, we've evaluated a wide range of models that I presented to you, and we've also proposed a standard, an evaluation protocol with that maybe I skip many details in this presentation for the sake of time. But you can find in the paper. And our experiments demonstrate that having the latent regulated autoencoder has a better performance compared to the standard version, especially when you have a training data contaminated. And we also underscore the pitfall of relying on outdated data sets because they may show you that your model is performing well, but to the current state of attacks and vector attacks, that may not be true. So you have to be careful about that. Thank you for your attention.
Thank you for the information.
I just have a question about you were saying that somehow managed to damage data. So how is the contamination get and how realistic you think that the feature space is not being with this drug?
Thank you for your question. Just come back to this one here. And yeah, so the way you contaminated the data sets here, we didn't manipulate the future. So it's not poisoning that may be the difference. We're not poisoning the data set, but manipulating the features, but we take because we take a data set that already contains network flow related to attacks, and then we take those attacks, we inject them into the training set, which should contain only benign traffic. So we are not manipulating the features in this setting. And this is realistic in the sense that let's say you collect your network traffic when there was already an attack going. So no change, because the problem with poisoning setting where you manipulate the feature, you may not be recover the traffic related to what you have after manipulating the feature. But here we are sure that those representations are really attacks, are really related to attacks, and then we inject them to the training set as they are. One training set is expected to contain only benign traffic, but by adding that, we are violating that assumption, and we wanted to see how the model perform in those settings.
Thank you very much for the nice information. I have a question, if I remember correctly, in the last question. So you do situation to figure out the pitfalls and these related with using all data set. Just wondering whether you find these pitfalls by exploring distribution shifts technology or
If I didn't get the last.
I mean, that's how you figure out these pitfalls.
Okay. Yeah. I mean, maybe the word is not well chosen there. So I was showing like here in the slots, different slots there. It's evaluation on all things, and with what you see here, most of the models they are performing good. They are good models, and this can be misleading. Why if you like develop a new model and you test them on the set, the case where the data set, the training data set is contaminated, you may think that your model is good, but that's not true, because those data sets are old, and the attack vector has evolved over the time. Like they are getting more complex, and which makes them difficult to be like attacks to be distinguished from what should be normal traffic. So yeah, relying on those. So the message here was relying on those old data sets can be problematic and not giving you good insights of how your model is performing. And we can see it in this projection that we have here. So you have clusters of attacks that they are clearly separated from the normal traffic compared to recent vector of attack where they really overlap. So yeah.
Okay, look at that. Two questions. Look like you need the new discount comes to be nine.
Yeah.
You should have you have between nine next the feature and feature. So maybe that's it.
They are coming from the same network. Yeah. Yeah.
Second question. You was expecting
Mayo?
So here you identify this why those as normal and the rest as anomaly.
Yeah.
So you define the normal distribution of I think. How do you define the normal and anomaly?
That's a good question. Actually, yeah, of course, doing anomaly detection, we expect anomalies to be the proportion of anomalies is less compared to the proportion of normal data. And if you look at the density here, you will expect traffic related to like normal traffic from your network to be represented in some density here. It should be many normal points in this area. We are compared to anomalies, they are pretty scattered and they are far apart.
Just because follow questions. Example flow is similar like less than a second. So you have to flow. Maybe the attack rate be much higher than we know. No, in that case, it will be as no one that attack rate.
Yeah, it's
Yes, bring back
I think with what we have done here, maybe it's something I should have mentioned. We really are in the setting where anomalies the proportion are anomalies higher than, of normal data. Yeah, so for that one, I don't think it's going to be the same, yeah, because those anomalies will influence them have higher density and then, the model will not perform.
Thank you.
Yeah.
This is the meeting.